Okay, so now that I've started recording, let's just go through everything again. So we're doing a quick recap of switching. So switching is our topic today. Uh, we know that there are two main types of switching, circuit switching and packet switching. There's only one thing that you need to know the difference between this. Circuit switching is dedicated. So you have a dedicated, you have a point A and a point B. You have a dedicated circuit between those 2 points. That is what is called circuit switching. In packet switching, there is no such dedicated link between the two nodes. Okay, and then when we further split these two parts, we get two other types. We have datagram, and we have the other one is virtual circuits, right? And so okay, so switching, we have two types: circuit switching, packet switching. Packet switching, you have two types: datagram, virtual circuits. What is the difference? Virtual circuit, it creates an illusion of a circuit. It's not really there, but it looks like it's there. And datagram, that thing does not exist. You have only packets that keep on transferring from node to node, right? In circuit switching, you don't have any more subpoints, so any more subcategories. But all you need to know is that it's dedicated. That's basically all that you have. So when we solve questions, there are only a few things that you need to know. And when we do questions, each time we do a question, we will learn more terms. Okay, so let's put let's start with today's questions. I am going to share the link of yesterday's session. The It's the YouTube link for yesterday's session. I don't know whether everybody received it, but I'm just sharing it again. This is a recording of yesterday's session. So let's start with today's. So this is our first question. We're given a path in a digital switch network has a data rate of 1 megabits per second. The exchange of 1,000 bits is required for the setup and teardown phases. The distance between two parties is 5,000 kilometers. Answer the following questions if the propagation speed is 210 raised to 8. What is the total delay of 1,000 bits of data exchanged in the data transfer phase? What is the total if so you have 1,000 bits, so you have black. Okay, you have 1,000 bits, you have 100,000 bits, and you have 1,000,000 bits. And what they're asking here is total delay for all these questions. And finally, they're asked find the delay per 1,000 bits of data for each of the above cases and compare them. What can you infer? Okay, so let's try and work to solve this question. The only thing that we're given here is that it's the only specification that we have here is that it's a circuit switch network, and we'll see how this matters. Oh, it's given here, setup and teardown phases. So that is what I was going to say. So how does circuit switch network work? So let's just quickly look at circuit switch. What is the setup and teardown phases? So I'm going to draw a little diagram here. I hope it'll clear out a lot of things. So let's say here we have node A, so circuit switching. Yes, and here we have node P. You have a setup phase and you have a teardown phase. So what I don't know whether you've learned handshakes yet, but a circuit switch is similar to a handshake, but not really a handshake. All you have is you have a setup. So you have data that goes from one node to the next. So this is, let's just put this S. So that's setup. And then from, let me draw that neatly. Setup. All right, so that goes from one to the other. S. And then you have another data transfer that happens from B to A. Okay, you got the straight line. So yeah. And this is basically an acknowledgement. It says, yes, we have a network ready. We can use this network. That's what that says. That's it. That's the setup phase. So this much was the setup phase. That's it. No double acknowledgement like in the handshakes that we see otherwise. And after that, you have another, and this is the actual data transfer. So let me just put that as D, data. Data transfer happens after the setup and the data. After the setup, sorry. And then once that is finished, the last phase is the tear down. So tear, tear down, T. And that's all. So when we're calculating the total delay, what is left? Okay, so when we're calculating the total delay, we need to calculate 1, 2, 3, 4 passes of data. So we have to keep all this in mind when we're solving this question. Okay, right. So let's begin. Um, yeah. Okay, so let's begin. What are what is the data that's given here? We can see that the data rate is one Mbps, that's 1 megabytes per second. You're given the total number of bits, 1,000 bits, and you're given the distance between the two parties, 5,000 kilometers. Right. The, what is the total delay if 1,000 bits of data exchanged during the data transfer phase? So let's calculate delays now. So delays. What all delays do we need to include? So we have 4 delays. So let us write it as, so you have one is all the setup things. So you have setup, acknowledgement, and teardown. And plus you have this transfer. I'm just going to write transfer. And transfer is dependent on how much bits you're going to transfer. But setup and acknowledgement are not. There's a transmission delay. There's, let me show. So when you're exchanging for setup and breakdown, you only need 1,000 bits. But when you're doing the transfer, that's when you need this 1,000 bits. So let's do for setting and tear down, setting up and tearing down, tearing down. What is the delay that we need? What is the delay that we have? So you need to transfer. So if you remember in yesterday's class, we discussed how to calculate transmission delay and propagation delay. Propagation delay is based only on the physical distance, right? So you have propagation. I'm just gonna write prop delay plus trans delay. What is that equal to? Propagation delay is only dependent on the distance, like we saw. So just let me recap this once quickly. So how do you find delay? So how do you find time? Time is always distance by speed, or let's say velocity here. That's how you're going to find. So when you have 5,000 and you have a speed, so you know how to calculate the time that it will take, the delay that it will incur. So you have 5,000 into 10 raised to how much? 3, right? Because it's kilometers. Divided by, we have the speed that is given here. Let's just quickly put that 2x 10 raised to 8. Now, what is the transmission delay? Transmission delay, again, you're using this same formula. This is the only formula, but you need to know for what you're going to use. You have 1 MB, you have given the length, the distance, like 1000 bits that need to be transferred. And what is the speed? This is the speed, the bandwidth, right? So transmission delay, where is it? So 1000 bits, 1000 divided by 1 Mbps. So how much is 1 Mbps in terms of only bits? That's 1 x 10 to the power 6, right? So I don't know what it will. Okay, so it does give some answer, but let's solve it properly. How would you solve this? So let's simplify this as, I'm just going to simplify it here, 6, 5 into 10 to the power 6, so that it becomes easier for us. So 5 divided by 2, we know 2.5 x, and so what would this be? 10 raised to minus 2 divided by, here we have 1000 divided by 10, 1 into 10 to the power 6. So let's just write that as 10. So we know this is 10 to the power 3. The answer here will be 10 to the power minus 3, right? Now what do we need to do? We need to divide. So when you simplify this, you should get how much? 2.5 x 10 to the power. So minus 2 will come up here. It will become plus 3 to 2.5 to 10 to the power 1, which is equal to 25. 25 what? 25. So we're doing everything in seconds, meters per second, everything. Oh, so yeah, propagation speed should be 2 into 10 to the power meters per second, not just meters. So it's seconds. So what did we just do now? What did we calculate? We calculated propagation delay plus transmission delay. That means it's for one journey from the source from A to B. For one journey, we calculated the delays. But we have 3 journeys before we actually, 3 journeys, we have S, A, and T, right? So you can say, let's put it as, it's not exactly setting up. So it's it's a network transfer. It's not a data transfer. It's just transferring to set up the network, right? So the total time, let's now we can put here, total time for setting up and tearing is going to be 3 times what is that? 3 into how much? 25, 75 what? Seconds. So now we have this S plus A plus T part. So total time for setting up and tearing, that's S plus A plus T. So that is 75. Now here one more thing to transfer, that is one more thing to calculate, that is the transferring time. So in all these questions, the total time for setting up and tearing will remain the same. What will change is the data transfer. This is D over here. How much time the D takes. So we need to calculate that for each subpart of the question that we have. Right. Okay. So we have 1000 bits of data. So let's calculate for the first one. The delay for data transmission. Transfer. Okay. What is it going to be? It is again going to have propagation delay and transmission delay. Propagation delay plus trans delay. But what is the difference here? So what is delay? Okay, so what is the propagation delay here? It does not change. So we still have 5000 and 2 to the 10 to power 8. So let's just copy that actually. Okay. What is the transmission delay? Bits by Mbps, right? How many bits? So we had 1,000 bits for the setting up, and for transferring also we have 1,000 bits. So it's actually going to be the same 1,000 divided by how much is the bandwidth? 1 Mbps. So 1 x 10 to the power 6. And we can see from this you're going to get the same thing. You're going to get the answer 25 seconds. Right? Um yeah. Have we done something wrong? Okay, anyway. Is there 2 into 10 as well? It should give us the same. Did we add something? Oh yeah, so we did make a mistake here. Yeah. So so 2.5, and then we did not add this part. Right? So there's more to this. We saw 2 into 10 to the power minus 2. It's not divided, it's plus 10 to the minus 3. Sorry about that. Right, so what answer would this give us now? So you have 2.5 into 10 to the power minus 3, so that's going to be 0.025. Am I right? So you're in ones and twos twice, yes, 0.0001. Right. So then here we would have, excuse me, 26. And how much would that be when you multiply? 0.078. 78 seconds, which is equal to 78 milliseconds. Right. So now, so what does this come to? This is the same calculation again get. So how much is this? So let's write equal to 0.026. This is also going to be 26 milliseconds. So what we were solving, sorry about that, I didn't say that we had divided A, this is the A part. Total delay, so what is this delay for data transfer that we calculated here? That is actually this D in the diagram. And what is this total time for setting up and clearing that we calculated? Let's write it here. S plus A plus T is what we calculate. That's how much? 70 milliseconds. Here we have, so D is equal to 26 milliseconds. Total delay. Now we know how to calculate this. So simply S plus A plus T plus D. How much is that? 78 plus 26. 104. 104 what? Milliseconds. That's it. That's how we solve the first question. The first part of the first question. So now let's quickly finish the other sections because we've already spent a lot of time in this. So P part. So here D small d is equal to how much? So it's going to be the same thing. 5 into 10 to the power 6 divided by the speed, 2 into 10 to the power 8 plus, but not 1,000 bits. How many bits are you giving? 100,000. So 100,000. Right? So how much is that going to be equal to? Here you'll get 2.5 x 10 to the power minus 2. Plus here how much will you get? So this is 10 to the power 6 divided by this 10 to the power, so 100,000, 10 to the power 5. 10 to the power 5 divided by 10 to the power 6, you're going to get 10 to the power minus 1. So simplifying that, that's actually 0.025 plus how much? 0.01. That's going to give you 0.035 seconds. Right? Now all that you need to do between these two is to add all these together. Total delay is equal to 0.078. Let me calculate. That's from here. S plus A plus T plus 0.035. That many milliseconds. That's how we can calculate the second part. For the C part, again we follow the same procedure. So D equals, what is the distance here? So it's again going to be the same thing. 5 into 10 to the power 6 divided by 2 into 10 to the power 8. So you have length, distance plus how many bits? In the C part, we're given 1 million bits of data exchange. Data is exchanged during the data transfer phase. So 1 million. So 3 4,000 and then 3 4. So that's 1 million. So 1 million, or we could just write as 10 to the power 6. So 10 to the power 6 divided by 10 to the power 6 is going to be 1. Oh, sorry. So this is 0.1, not 0.1. And this will change as 125. So 125. So what's that equal to? 2.03 milliseconds. Sorry about that. So, okay, let's solve. So this is going to be again 2.5 into 10 to the power minus 2 plus how much? So here we have 10, you have 1 million divided by 1 million, it's going to give you 1. How much is that? So 0.025 plus 1, 1.025. 1.025 seconds. So total delay, all that you need to do, you have your S plus A plus T here, you have the D value here, just need to add these two. So 0.078 plus 1.025 is equal to 1103, 1.103 seconds. Okay, so this was also seconds, not milliseconds. That is our answers for the first 3 parts. Now the final question, final subpart is find the delay per 1000 bits of data for each of the above cases and compare them. What do you infer? So we're asked per 1000 bits. How will you solve this? We know for, let's take the first part. Let's start with the last part, the one that we found. We know that for 10 to the power 6, so for 10 to the power 6, 1 million bits, it takes how long? 1.103. And for every 1000 bits was asked, so 10 to the power 3, how much time will it take? That is the question that they have asked. And simply, as you can see, you're only going to divide to get the answer. Okay, so let's solve this part of the thing also. So D part of the question, D part, D subsection. So for part A, how much was the total delay? 104. So let's keep it as milliseconds. So 104 into 10 to the power 3 divided by, how much was the bits we had here? 1000. So 10 to the power, again 3. You can see that's again going to come out to 104 milliseconds. For B, what was the answer that we got? Let's write in milliseconds. 203 milliseconds into 10 to the power. How much did we have? We had 100,000. That subsection had 100,000. So 10 raised to 5 divided by, again, 10 raised to 3. And that's going to give us this much amount of milliseconds. And finally, for C, oh, so sorry, I mixed up the exponents. So this is 3 and this is 5. 5 is equal to that much amount of milliseconds. And finally, for the last part, we have how many milliseconds? What did we calculate? We found, so this, so 1003 milliseconds x to the power 3 divided by 10 power 6. How much is that going to be? 120 ms. So we have solved the third part also, the fourth part also. What do you infer is the only last thing that's in this question. So what do you infer when you look at these things? Clearly, you can see when number of bits is more. So in the last section, we sent 1 million bits. The rate at how long every 1,000 bits will take is much less. What this means is we spend so much of time trying to set up this network, right? But we sent so little data in the first part, let's say 1,000 bits. It was not worth it. But when we had to send 1 million bits, it was worth doing this whole connection. It was worth, because every 1,000 bits only take 1 millisecond. However, this is like an average of every 1,000. So on average, every 1,000 bits, or for example, you could say for every kilobit, the average speed, the average time a kilobit would need to get transferred was only 1 millisecond. But in the first case, it was 100 milliseconds, 104 milliseconds. So that's the inference that they are looking for. Okay, so quick recap. This is how you needed to know how circuit switching works. You needed to know all the delays. So you have, so let me write this here as D, so it matches with the diagram. So you have S plus A and T and D. S plus A plus T, one transfer just S is propagation plus trans delay, then we multiplied by 3 because you have S, A, and T, and we got 78. Then for each transfer, the D, again we calculate propagation transmission delay. Transmission delay is related to bits. So we changed the bits and we got 26. We added that with the original. Then here we got 125. We added it with the original. Here we got 1. We added it with the original. Then we compared. We found how much is 10 to the power 3 would take. And we found some inference. Okay, let's move on to our next question. Question 2. Find the output port for the packets with the following destination addresses. This is actually an important question because it's there in a lot of papers. Even when I was studying computer networks, I remember having this question in my PAT exam. Find the output port for packets with the following destination address. And you're just given some packets and some destinations, and you're given this table. This is a very simple question. You cannot get a simpler question. You're given destination address. What is the destination address? What output port it should come out. So simply is just matching between the two. 7176, match it to. That's your answer. Packet 1 goes to or through port 2. That's all. So we can quickly finish this question. It's a very simple question, but you you need to know what what this table is, and you need to know how to read this table. But once you know that, you can answer everything correctly. Packet 2 goes through. So 2 is 1, 1, 2, 3, 3. Output port is 3. So goes through port 3. Packet 3, 8766 goes to which port? Output port 3. So packet 3 goes through port 1, 2, 3, 3 goes to 3. Sorry, 8766, so 3. Yes. Packet 4, where does it go? 9144. That's connected to which one? Output port 3. So port 2. That is all in this question. That's all that you need to do. You don't need to remember anything actually. You just have to see. It's all about matching. So see what the destination address for the packet, and then see where the output port is. So how what is the use of this kind of question? Like what is the use of having something like this? Because basically when you have packets, so you have. So I know this is a simple question. Just to mention what is the use of this, and then we can move on to the next question. So a packet wants to be sent to C. So this is the links between the nodes. A packet wants to be sent to C, but in packet switching, that packet is only reached till here. It will not. There's no direct connection till C. When it reaches here, B will see that its destination is written as C, but doesn't know where is C. So it will see its table and find, okay, for whatever destination, this is the port that I should send it to. And it'll read its table. So let's assume this is its table. It'll read its table and then it'll forward that packet to C. And C will finally get where it needs to be. The packet will finally get where it needs to be. That's all. So it's a good question. There's something that can be asked, but it's a very simple question. Okay, let's move on to the next question. Question 3. This is again, so we're having the same thing as propagation, transmission, all these things we have. But, let's just read this question. 5 equal sized datagrams belonging to the same message leave for the destination one after the other. So you have 5 datagrams, like 5 packets that need to go to some places. Right? However, they travel through different paths as shown in this table. So you have the first packet, second, third, fourth, fifth, how long that path is. So see, this some are like 3,000 and some are going all the way to 12,000. And what are the switches? What does it mean? Like, so the packet is going from one switch to another before it reaches its destination. Assume for the delay for each switch, including waiting and processing, is 3, 10, 20, 7, 20 milliseconds respectively. So respectively, what does that mean? For each switch, each of these switches, each one has their own delay. It's not constant. And we're asked, assuming that the propagation is 2 into 10 raised to 8, find the order the datagrams arrived. So this is a good question because of this. That's what's going to make this question likely to be asked. Find the order of datagrams arrive. Find the order the datagrams arrive at the destination and the delay for each. You need the delay if you need to find out who came first. Ignore any other delays. So normally, we had delays is equal to propagation plus transmission. Propagation. Yes, yesterday also we had this problem. So delay is equal to propagation plus transmission. What is transmission? Bits per band. Is there any bandwidth mentioned in this question? No. And they have told us ignore any other delays in transmission. So we can safely ignore this transmission delay. But another type of delay is being asked here, was mentioned in this question. That is the switching delay. This or the switch delay. What is switch delay? So basically when you have a switch and it receives a packet to datagram, it will first process it, and then the datagram goes it in a queue, and then from that queue, one by one, each packet will be sent out. So this in total is what they've called delay for each switch, including waiting and processing. So it's basically a queuing delay and the processing delay. Right? So that's queuing. So we have here, we're asked, we don't need to calculate transmission delay, but we need to calculate propagation delay and switch delay. So it's now actually a very easy question. So let's finish it. So for datagram one, we are given the propagation delay. What is propagation? You've seen in so many other questions. They didn't go. Propagation is length divided by speed. So datagram one, propagation. No, so propagation won't change for everything. So actually, we can write for all datagrams. For all datagrams, propagation delay is equal to the length divided by the speed. So what is the length here? Oh no, sorry. So each datagram has their own length, so we can't write for all datagrams. Sorry about that. So for datagram one, we have length 3200, so 3200 kilometers. So let's put it into meters divided by how much is the speed? 2 into 10 raised to 8. So 2x 10 raised to 8. How much is that going to give us? So let's simplify. That's going to be 32 x 10 to the power 5 divided by 2 into 10 to the power 8. So you can see how this is going to be. It's going to be 16 into 10 to the power how much? Minus 3. So we can basically write that as 6 km, so 16 milliseconds. That's all. Now how much are the switch delays? Switch delays. What are the switch delays? So we have 1, 3, and 5. What are the switch delays? 1 has 3. So let's write 3 plus third switch. Third switch is how much? 20 plus 5. 1, 2, 3, 4, 5. 20. That's 43 milliseconds. That's it. Now total delay is equal to 16 plus 43. 59 milliseconds. Simple. So I think we have to calculate for all. So let's quickly calculate. Or we can do like let's so the second and third one is they're all going to be in the same format. So let's just quickly put datagram 2. So let's put it together. So delay is going to be, what is the distance? 11,700. So 11,700 kilometers into 10 raised to 3, 10 raised to 3 divided by, so again 2x 10 to the power 8. That's going to be that. And then the switch delays, how much is that? So 1, 2, and 5. So 3 plus 2 is how much? 10 plus 5. 5 is how much delay having? Just having 20 plus 20, 33. 33 what milliseconds? And this is, no, it's 58.5 milliseconds. That the total delay is how much? Total delay 33 plus 58.5, 91.5 milliseconds. For datagram 3. Prop delay. So this is prop delay, not just delay. Is equal to, so I'm just going to copy from here. 11,700. So it's not 11,700 here, it's 2200. And that's equal to that many seconds. And the switch delay, what are the ones that we given? 1, 2, 3, 5. So this is a lot of things. So 3 plus the second switch has how much? 10 plus 3 again, says 20. Plus the fifth switch, which is again that many milliseconds. So the total delay, we have 61 milliseconds on the first part plus 53 milliseconds. You have a total of how much? 114 milliseconds. 2 more to go for datagram 4. P delay, $10,200 here, so 10,200. That's that many seconds. And S delay. So what are the switches? They're given 1, 4, and 5. So 1, which is 3, 4, which is 7, 5, which is 20. So that's 30 milliseconds. So total 30 plus 51, 81, 81 milliseconds. Okay. For datagram 5, so this is our last one. I'm just going to copy everything. So we have 10,700. So 10,700. The delays here are going to be 1, 4, 3, and 5. So 1, 4, 3, and 5. 1, which is 3. 4, which is 7. 3, which is 20. So see, here's an example of switches that are not in order. 1, 4, 3, and 5. It is possible. And 20. That's 50. So this will become 50 plus 53.5. Yes. Now, why did we calculate all this? We calculated all this so that we could answer this question. Order the datagrams arrive. So which one do you think will arrive the first? So clearly it has something to do with delays. the one with the least delay. So they're all sent from the same. They sent for the destination, the same destination file, but the distance that the paths that they take are different. So who will reshare the first? The one with the least delay, right? The one with the least delay will be first. So which one is that? This is one. This is the first because it's one. Next, which will come 4. Next, which will come this one, and then finally this one, and then last this one. This third, fourth, fifth, and this is the second. Right? So let's recap. What did we do in this question? The reason why this question is important because they said find the order of the datagrams and they give us a bunch of delays. We know that delay is usually propagation plus transmission, but this time they gave us no bits, no bandwidth, nothing, and they told us to ignore other delays, so we ignored in transmission. Instead, they gave us another kind of delay, the switch delay, and that for each switch had a different delay and included waiting and process. Right? So what did we do with this? We took propagation delay, which is the path divided by the speed. We found that we took the switch delay, which is for each switch. What is the respective delay? We took that, we added that, found something, then we added the propagation delay to a switch delay, and we got this answer. We continue that for all the 5. If I answer the order, whichever had the least delay will arrive the first. Right. So what you can notice here is that the second one 11,700 and the fourth one 10,200. So it's almost, so not the fourth one. So the fifth one was fourth. Fifth one was 10,700, and that before that came the second, which is 11,000. So what I'm trying to say is, even though the path length was longer, it arrived before another. So in networking, it's not always about the path length because you have to. Path length is important when we do digitize algorithm. When you find the shortest path, it is important. But when you have packet switching, you need to keep in mind the amount of delay that you're going to face in each switch, right? Because if the switches have delays, that would delay your packet. Okay, that was this question. Let's move on to the next question. So we are nearing an hour. We have a lot more questions to do. I'll try to move a little faster the second hour, but okay, I will try. So let's take a break from the problems now. Let's do a theory question. So again, where are these questions from? I cannot stress enough. It's official textbook. What is the official textbook? Read the Perros book. So Perros's book. That's one book that's very well explained. It's the official textbook for this course, and that's something that it's a good textbook to read. And most of these questions are from there. It's also a favorite of the teachers because when you're looking to set questions, they can look at the textbook and they're likely to look at the textbook. Okay, answer the following questions. Can a routing table in a datagram network have 2 entries with the same destination address? Explain. Sorry, explain. Yes. And in part B, we are given, can a switching table in a virtual circuit network have 2 entries with the same input port number, with the same output port number, with the same incoming VCI, the same outgoing VCI, with the same incoming values port VCI, with the same outgoing values port VCI. It may seem like there's a lot, but it's actually not a very difficult question. You just need to know. Okay, so let me take out this. What do you need to know? Routing table, two types of tables again. Routing table and switching table. Switching table, correct? What is a routing table? Routing table is destination addresses. You have your packet sees a routing table. It should know where it should be routed to. So routing table is all about destination addresses. What about switching table? So in switching table is a little different. It does not have a destination. So routing table. So switching table is in virtual circuits. Switching table has two entities. You have a port. So this is something that you need to know if you want to be able to answer this question. You have a port and you have a VCI. What is a VCI? Virtual, V for virtual, C for circuit, I for identifier. So we know when you have virtual circuits, when a path is made from one, let's say A to B. In virtual circuits, it's not really a circuit, it's a virtual, but it's given an identifier. Correct? So one unique row in a VCI in a switching table would be this PVCI that they mentioned here also. So port VCI. So I'm just gonna write VCI. This is what gives uniqueness to this row. Whereas in the routing table, what gives uniqueness? Only the destination address. That is it. That's all that we need to know to answer this question. So let me write that a little bit clearly, a little bit clearer. VCI. Okay, let's begin. So let me. Okay. Can a routing table in a data network have two entries with the same destination address? No, it cannot, because destination address is the main thing in the routing table. If two, what would happen? Let's say if two entries had the same destination address, so you have, if it's packet A sent to C, then you have, if it's a packet A sent it to B. So where should it go? C or B? It will not know. That's why it's not possible for a routing table to have two entries. Let me write it clearly. So like our answers. Answer is A part. No, nothing else. Okay, B. Can a switching table in a watch have two entries with the same input port number? We discussed this. So we have a port number here, we have a port number here, we have VCs here, nothing matters. What should be unique is the combination of PC and P and VCI. So that's simply a no. So B part, so what do I write? So I write switching table. So in that A part is no. What with the same output, no, output port number. Again, port number doesn't matter. No. With the same incoming VCIs again doesn't matter. What matters is the combination. So also a no. With the same outgoing VCIs again no. So they're testing with the incoming, outgoing. With the same incoming values port VCI, it does matter. Oh, so sorry. This would be yes. So can a switching table have? Yes, it can have. Can it have the same port? Can it have the same? This is all yes. Can it have with the same income with the unique combination? No. And unique combination of outgoing? No. Because all that you have to remember is that this thing should be unique. You cannot have the same way in routing table how you cannot have the same destination. In switching table, you cannot have the same this double port VCI. It should not be same. It cannot be same because if something comes, it doesn't know which network to go to or which port. It needs both the port and the VCI. So if two ports are the same, it'll see what is the correct circuit that I need to go to, and based on that, you can decide. Or if two VCIs are the same, based on the port, they can decide where to go to. But if port VCI has another entry with port VCI, now it doesn't know which one to follow. That is all. So that was a quick theory question that we saw. And it's basically it all comes down to you knowing what is a routing table, what is a switching table, what makes something unique in that table. Okay, fine. Let's go to the next question. Q5. Hmm. We can do another theory question. Then we can solve after that. We can do some more problems. Okay, let's read. Answer the following questions. Why does a circuit switch network, okay, need end-to-end addressing during the setup and the teardown phases? Why no address is needed during the data transfer phase? So let's go back to the diagram that we drew. Where was it? Yeah, so you have setup. These two, this whole together is called setup assigning. And then you have the teardown. Why would you need addresses here and not in the data transfer phase? And the answer is actually very clear, but let's read the other part. Why does a datagram network need only end-to-end addressing during the transfer phase, but no addressing during the setup and teardown phases? Why does a virtual circuit need addresses during all three phases? It's a little twisted question. So they want to confuse you a little bit. Why does so what we saw here? What happens when so the first question? So what happens when you do that first? Is you get that acknowledgement that we have a connection now. What happens now? Right now you have dedicated you have a dedicated circuit connection. Do you need to know who's over here, who's over here, what node is over here? You don't need to. Because once you have this connection, it's like a road. You can just keep traveling on that road because you're sure that that road leads to the correct node. So that's here. So if we were to answer this, we would say addresses are needed because a connection connection needs to be set up. After the connection is set up, no address is required. Okay. What about the second part? So this is A part. What about the second part? Why does datagram network need only end-to-end data transfer, but no addressing your setup and error? Here is where they have done a tricky thing. During the setup and the teardown phase of a datagram network does not have setup and teardown phase. We have setup and teardown so that we can build this road from point A to point B, this node. But datagram network does not have any path like this. And so actually the answer is that it doesn't need, oh, so let's just say there is no setup and teardown phase in datagram network. Because datagram network, each time it hops from one switch to the next switch. That's why it's called connectionless, right? Okay. The last part is, why does a virtual network need addresses during all three phases? What happens in virtual circuit network? So just now we saw this is virtual circuit network where you have a switching table, P, VCI, everything. Is there a connection? Is there a dedicated network in VCI? Yes, but it's not. Sorry about that. Let's continue. Um, Virtual circuit network does have a circuit that from point A to point B, but it is not dedicated. And if you have a circuit like this, that means you have a setup and a acknowledgement phase, right? So what happens in that setup acknowledgement? You make the switching table. So we would say PCs need addresses for making the switching table. But what is the last phase? Data transfer phase. Do we still need addresses? Yes, we still need addresses. Why? Because so we still need addresses during data transfer because we don't have a dedicated road like this. So there's no dedicated road that you can just travel on and let the data travel from A to B because there is no dedicated connection. Instead, the packet relies on the switching switching table. So that's why it still needs to carry the address, destination address. And to look at the switching table, see what is the VCA that it needs to go and then go on that. So to recap, circuit switching, you have this setup in this phase here. You need it during that, but once you have this dedicated channel, you don't need a destination, you can just travel in that channel. Datagram, there is no setup and data. Every time you transfer from one to another, you need destination because there is no channel, no fixed road. Virtual circuit is a combination of both, right? So you have setup, so you need destination for it. And for transfer, it's not a dedicated channel. You still need to know the destination. So you need to have the address. Okay, let's move on. So what can we do? Okay, this is a good question. It's a oops. The good question because it introduces a new topic that I have not discussed in UTS sessions before. Question is a cross-country fiber of 10 gigabits per second bandwidth and 40 milliseconds delay can hold how many bits? So this is where we learn an important topic called delay X bandwidth. The, or it's also like this is the product of delay and bandwidth in a network. What does that mean? An easy way to think about this is so delay is like time, bandwidth is like speed. What happens when you multiply this? You get the distance. So how many bits can be held inside a channel is always equal to how much delay is there into how much bandwidth the channel can support. Okay, so how will we solve this? So let's write solution. Delay, what is the delay? 40 milliseconds, nothing to change. Oh, we can change it actually. We can put 0.04 seconds. Bandwidth, bandwidth. How much is that coming to? 10 gigabits per second. We're not seeing this unit also before. 10 giga. So you know mega is million, giga is billion. So 10 raised to 9 bits per second. How many bits are right? Or just we'll just write delay expand with how much is it going to be the multiplication of these two. So 0.04 times 10 times 10 to the power minus sorry positive 9. That is going to be 4 into 10 to the power 9. Right, so let's say 2 bits of this went to remove the decimal point, we left with 7 8, so it's 4 into the power 8 bits. That's it. Short solution to a short question. 4 into 10 to the power 8. That is the answer. That's how many bits can be. That's how many bits it can be uh, stored in this fiber. Or we could also write this in more. There's actually 400 10 to the power 6, which is actually 400 megabits. Or whatever you write, make sure you write the correct unit. So that's the solution for this question. So what is the thing that I wanted to show was delay into bandwidth product. That's the important thing because that gives us the distance. So that's like the how much can be stored inside this channel. So all that we need to remember is doing the delay and delay into bandwidth formula. So that's how we solve this question. Okay, let's move to the next question. So question 7. Let me bring the question up here. Yeah, Sean. Let me increase the size. Okay. We consider a point-to-point link 4 kilometers in length. At what bandwidth would propagation delay at a speed of 2 into 10 to the power 8? So this is 10 to the power 8 equal transmit delay for 100 byte packets. What about 5 12 byte packets? So what is asked in this question? You're given a length you're given a delay, and you're given you're given the propagation delay, and you're given the transmission delay. So let's recap what we had done. Even in the previous session, we did a similar question. What exactly is transmission delay? Transmission is you have number of bits and you have the bandwidth. So I'm just going to write B D. What isn't there in propagation? Give me a minute. Okay. Yeah. So what is there in propagation? You're looking at the length divided by the speed of light. And write this a little bit more clear. This is bit. P. Okay. So they're asking us at what bandwidth would they be so when will propagation delay equal transmission delay for 100 byte packets? Very simple. So let's represent bits by BT. So BT divided by bandwidth. So PW. When will that be equal to L by S? And what are the things that are given in this question? So length is given. How much is given for what is S, the speed? How much is that given? That is also given 200 times power 8. The bandwidth, is that given? And they're asking us at what bandwidth. So that's the thing which we need to find out. So that's the question. Bits given? Yes, bits is also given. They're given it in terms of bytes, so we can convert it. So given us 100 bytes. So let's solve the first part of the problem. So A part. How many bits? You're looking at 100 bytes. So converted to bit, we'll multiply by 8 divided by bandwidth. So bandwidth we don't know. So let's leave it as BW. Length, what are you looking at? 4 kilometers. So 4. So let's write 4,000 meters. Speed, what do we have? We have 2 into 10 to the power 8. And that's it. If you simplify, when you simplify this, you will get a bandwidth. You will get the bandwidth that is required in this. And the second question, or we can just quickly solve this. So we can see the LHS is going to be 800 divided by bandwidth equals. So this will be 10 raised to 3, 10 raised to minus 5 will come, so it will be 2x 10 to the power minus 5. And then you could take this bandwidth could come to that side, cross multiply, you're going to get how much? 400 x 10 to the power 5 is equal to bandwidth. Is equal to bandwidth. What is this 4 into 10 to the power 6? Is actually 40 megabits per second. That's all. That's the first part. What about the second part? B part. So let's solve the B part. B. Again, we're asked the same thing, same propagation delay, same link, same everything same, but only bytes has changed to 512. So instead of 100, we have to put 512. So 512 into converting it into bits, multiply by 8, divided by, so here denominator BW is equal to length, again 4,000 divided by propagation delay 200 10 to the power 8, 2x 10 to the power 8. Okay, so once we simplify, we can get the answer for band. So how much is 512 512 into 8? That's going to come around 4096. And on this side we're going to get again W. So what is it going to be? So 10 raised to 3, 10 raised to 5, 2 into 10 raised to minus 5. And then when we cross multiply this, it's going to be 4096 divided by 2. It's So it's not C part here. 2048 into 10 raised to 5 is equal to bandwidth when we cross multiply. So bandwidth is how much? This can be rewritten as 204 megabits per second. That's it. That's how we solve this question. So the answer you'll have to put is 40 megabits per second. And in the second part, you will put 204. Also, we forgot the 0.8, so 204.8 megabits per second. So let's quickly recap what we just did. They asked us um, at what bandwidth. So they want propagation delay equal transmission delay. We saw in all the previous, so many previous problems that we did, everywhere transmission is bits by the bandwidth. That could be BD here, but it's what I meant right is BW, bits by bandwidth. And propagation delay everywhere is L by S, so length divided by the speed. When will they become equal? Just need to equate the two. Bits by bandwidth equal length by speed. Here you bits. So bits is what first part and the second part bits. Length is the same, speed is the same, do everything, solve it, you'll get the answer. 40 megabits per second and 204 megabits. Okay, this is a simple question. Let's move on. Let's move on to the next. So that was our seventh. We have now question 8. Mm, this is, so let me just format A part, B part, C part. Okay, so suppose a 128 kilobits per second point-to-point link is created, is set up between Earth and a rover on Mars. The distance from the Earth to Mars when they are closest together is approximately 55 gigameters, and data travels over the link at a speed of light 3 into 10 raised to power 8 meters per second. Calculate minimum RTT delay bandwidth. Cameras on the rover takes pictures of surroundings and sees to Earth. How quickly after a picture is taken can it reach? So first part is just round trip RTT. So you should know what RTT is round trip time. What is that round trip time? So RTT, you have one node here, one node here. How long will it take to get from here to there and then back? That's round trip time. Delay X bandwidth, we solved. This is why we solved the previous question on delay X bandwidth. So that was how many bits can be held in a fiber given by delay X bandwidth. So delay into bandwidth product is, it could be asked like how many bits can be stored in this cosmic link, right? But they've asked us delay X bandwidth. Okay. Camera so basically you have something, you have a camera, so say this is Mars, this is Earth, you have a camera on Mars. How long will it take to get the info from camera from Mars to Earth, assuming that the data is 5 megabits per second, 5 megabits. Okay, how can we solve this? So RTT, the round trip time, is basically going to be propagation delay into y. You want delay to go from Earth to Mars and one delay to go from Mars to Earth. That's all that you need to do. How do we calculate propagation? So we've seen this in so many questions. Even the previous question, length by speed. What is length here? 55 gigameters. So this is the first time we're using gigameters. So 55 into 10 to the power, excuse me, 10 to the power 9. Speed, whatever is given, not 2 this time, they've given us 8. Right? How much is that going to come to? So let's get one note to calculate. 183.333. So what is it going to be? Meters per second. So this is going to be seconds. So that was not that's not RGT. That was pro delay. Delay. So what will RTT be? Simply you don't have to do anything. Just multiply this twice. So 183.33 times 2 seconds. That's it. That's your answer. 366. So that was part A. RTT calculation. If we just need to find the propagation delay, and you can quickly solve RTT type questions. Okay, let's go to the second part. Delay times bandwidth. Delay times bandwidth. In this, we have they've not given us directly the delay. They've said they've given the bandwidth. So we have 128. So that's done. But for delay, we need to calculate it on our own. I think yes, we do. So that's going to be delay again. So we actually calculated it in the first part. So it's 183.33. Now what is the bandwidth? 128. Okay, so bandwidth is kilobits. So we need to do 10 to the power 3 because it's kilo. That's it. So we're getting 23,466,240 40 what bits, because 183 that is in seconds. What is this? 128 kilobytes per second. So finally answer is going to be in bits. So or you can write this in terms of more general form. 23.4, let's round to 47 megabits. That's it. That's what. And how would you convert this to bytes? You just divide again by 8. It should come to around like 2 point something megabytes, but this is good enough. Okay, that was the second part. Let's see third part. This is they've given a scenario. You have a camera on the rover on Mars that's here, and you're sending it back to Earth. How quickly after the picture can it reach Earth? Given this. So this is a proper total delay question. And in total delay, we calculate propagation delay plus transmission delay. Propagation delay we have calculated in all the all the previous questions. 183.33 on the first part that we calculated. And we won't use RTT, right? Why are we not using RTT? Because RTT is for both going and coming. And this is just one, they were just asked, picture is taken, it will reach Earth, so that's only one. Okay. What is the transmission delay? Transmission delay, like we saw previous question, again, bits by bandwidth. So bits by bandwidth. So we can just put in the value. So 5 MB, okay, 5 into 10 to the power of 6 bytes divided by how much do we have bandwidth? We have 128 kilobytes. So 128 x 10 to the power 3. That's it. Now, so let's we can solve this. So 183 will continue to be 183, and 5 divided by 128. So we can use a calculator. 120, if we do 5 divided by 128, you're getting 0.039 on my calculator. And what is the power going to be? 10 raised to 6 divided by 10 raised to 3, 10 raised to 3. Clearly, you can see this is actually going to be 39. So, but let's do that in the next step. That's 183.33 plus 39. That's your answer. 222. Right. So I think we have solved this properly. So we had transmission delay, just 5 megabits, yes. We converted that into total number of bits. We put in divided by bandwidth. We got this, we did this, we added propagation transmission delay. We got this. Okay, so that was the calculation. So let's quickly recap on what we did. They gave us bandwidth, they gave us length, they gave us speed. RTT is simply propagation delay into 2. We put the values, multiplied by 2, we got RTT. Delay into bandwidth they already gave. Delay, we calculated in our first. So we got our answer. Total delay for a particular case, we have propagation, which we already calculated before. Transmission, they gave us a particular case, they gave us number of bits 5 MB. Although an image should be megabytes probably, but we took 5 megabits. That's fine. We had bits divided by the total bandwidth. We found their transmission delay, we added it, and we got our final answer. So that was how we did this question. The new things, RTT was something new. Rest everything was new forms of the formula. If it helps, you can have some diagram like this that will show transmission times. Okay, let's move to the next question. Question 9. Hmm. This is a question that is likely to be questioned, likely to be asked in an examination. So it's a scenario that is given, and you're asked what to do. So let's read. You are asked to develop switching network for a university in building 1. So you have a building 1, 4 telephones are available and connected with the 4x4 switch. In the same building, so you have some more buildings, 2 and you have 3 have telephones with 2x2 switches each. So you have 2 here, 2 here, put that in another color. So you have two telephones here, 2 telephones here. 2x2 just means that, so you have 2 telephones and you have 2 switches. That's what it means. And you have 4 here. Now the question is, assume communication is made through 4 kilohertz voice channels and suggest an appropriate switching technique. So here you have only 2 switching techniques to choose from. So you have either circuit switching or packet switching. Which would be used? So you need to know that telephones are always but were originally and even today, most telephones that they're circuit switching. Circuit switching means you have one place to another. It's a dedicated line. And if somebody else tries to call using a telephone, somebody else tries to call, he'll hear line is busy, person is talking to somebody else. He cannot join in on that talk. However, today, we don't use telephones. We use like internet or voice over internet. In that is not circuit switching, that is packet switching. So that's why people are able to join. Packets can be routed wherever they want to be routed, wherever they need to be routed. But in traditional telephones, it's only circuit switching. So actually, your answer for most of appropriate switching technique would be circuit switching. And why I wanted to talk about this question is because of this four on one side, two on another, because it resembles a diagram that we have in our textbook. I'm just going to paste that diagram also here. So this is a diagram in our textbook, the one written by Bears. Why am I showing this? Because it's actually an exact description. This is this question is a description. This question is a description of this diagram. Where you have one building, you have building one, building two, building three. So let me just put here one, two, three. Building one has four telephones, building two has two, building three has two, a 4x4 switch, 2x2 switch, 2x2 switch. If, for example, they asked draw a diagram also, your diagram would look something like this, where every switch, so you have these main switches in the network, every switch is connected to this, and also every switch over here, these two is connected to the central. What are these arrows? That's the flow of data. So data is flowing towards those central switches. So this is a good example of a circuit switch. So if you were asked to draw a diagram, you would draw a switching network like this. Okay. So what did we see in this question? All we were asked, we were mentioned telephone. So that was a major keyword. And they were asking which switching technique will you use? When you see telephones, it's a good idea that you should choose circuit switching. So the circuit switching gives you that dedicated channel between one node and the other. Yeah. Packet switching, on the other hand, is popular now because of the internet and the voice over internet protocols that we have, but telephones were circuit. And this is what it would look like when you had a number of buildings. You could have, instead of one, here two buildings with two, and you still have a similar diagram. So here we have two, here two, right? What is the use? So even the voice, so what is this 4 kilohertz voice channels doing? So you can see here, every channel here has 4 kilohertz. This is actually FDM, frequency distribution, um, frequency divided. So the total, each one gets 4, 4, 4, 4, and so these main switches, which has to accommodate all these switches, it has like the max, which is 8, because you're getting from this side and from this side. Yeah, that is all in this question. So let me write the answer here. So it's not packet switching. So answer circuit switching. And I'll share this document after this class, this session. Okay, let's move on. So I think this might be our last question. Hmm. Okay, so this is an interesting question because it has some new, again, new concepts that are actually out of syllabus, but we're still able to do this problem with what we know. Question is calculate the latency. Calculate latency from first bit sent to last bit received for, so basically they're saying total delay. So you need to account for everything. 1 Gbps Ethernet with a single store and forward switch in the pack in the path and a packet size of 5,000 bits. Assume that each link introduces a propagation delay, okay, of 10 microseconds, and that the switch begins retransmitting immediately after it's finishing. So basically, they're saying there's no processing time, it'll send. Same as in A, but on three switches. So here we had how many switches? We had singles. So you had one switch. Three switch, asynchronous switching plus cut-through switching. It is able to. So here the B part, C part, they're saying three switches, same as B, but assume cut-through switching. Now, this is something we're not seeing because we've only seen circuit switching, packet switching. But they've explained what cut-through means. It is able to begin retransmitting the packet after the first 120 bits has been received. So normally what happens in normal packet switching let's say these are two switches, switch, data comes, the switch will wait for the full data to load and then only it will transfer to the next. But in cut-through switching, once the first 122 bits comes, that's it, that's enough. It'll transfer those 122 bits to the next. That's the only difference between normal packet switching and packets, cut through switching. So how will we solve this problem? So we asked for latency. Okay, so latency actually this might you might have had to include this in the previous session when we discussed parameters. But let's talk about it here. Delay, like we've seen in all the other um questions, delay is propagation delay plus transmission delay plus any we saw in one of the questions we saw switch delay where it was it was in this question where we saw something called switch delay also. So let's just write switch delay, but we know it says here switch transmits immediately, so there is no switch delay. But what we have is propagation and transmission. Propagation is given 10 microseconds. Transmission is not given. So let's calculate the transmission delay. Again, transmission we know bits by bandwidth. How many bits? 5,000. How many? What's the bandwidth? 1 gigabit. So 10 power 9. That's going to give you 5 into 10 to the power minus 6 seconds. Right, so gigabits was in per second. This is also seconds. Okay, that's basically 5 micros. So let's just write u seconds. Okay, now let's the diagram of, so first bit sent to last bit received. So it's not just switching. Let's look at the whole diagram. So you have a sender, you have a switch. So let's put this W switch, and you have a receiver. First bit is sent to last bit received. So you have to look at the whole network, including sender and receiver. How many links are there in this network? 2, right? So the total transmission delay of this entire network would be 2 into the transmission delay of 1 link. Same way, the total propagation delay would be 2 into the propagation delay of 1. So what do I mean? What I'm saying is the total delay from, let's say, first bit sent to bit received, FPS to LBR. That's going to be 2 into, so this one will have propagation plus transmission, so it's the delay. So we're going to delay of 1 link. How much is that? So that's equal to 2 into, how much is the delay for 1 link? So propagation plus transmission. Propagation is given here as 10 microseconds, plus how much is the transmission delay? 5 microseconds. So you can see this is going to calculate to 30 microseconds. That's it. That's the answer for the first part. All that you need to remember is this diagram, because it's not usual to calculate from the sender to the receiver. Usually we just calculate from switch to switch. But questions can be asked like this. In the B part, same as A but with 3 switches. Okay, so we need to draw one more diagram. We have sender, switch 1, switch 2, switch 3, and the receiver. Link here, link here, here, here. So how many links in total? 4. Here you had just 2 links in total. So okay. So now what would be the difference? Instead of multiplying by 2 for the delay of 1 link, you'd have to multiply by 4. It's actually very easy. So let's quickly finish this part also. So total delay from yes to LBR is equal to 4 into delay of 1 link, which is equal to 4 into 10. Yeah, 10 microseconds plus 5 microseconds. So you can clearly see that this calculation is coming to 60 microseconds. That's all. That's the second part also answered. Okay, now let's go to the final part. Part C. Part C. What does it say? Same as B. So we have 3 switches, but assume cut-through switching. That means it is able to begin retransmitting the packet after the first 128 bits have been received. So I showed like normally it'll wait for the full packet to send it, but now you're just getting 120 bits. That's enough. Send. So what does this mean in the network? So so to understand that, we need to look a little bit about these two delays. What is propagation delay dependent on? It's dependent on the length. It's dependent on the speed. Are any of these changing in cut-through switching? No. Length is still going to be, oh, it's not given here. So propagation delay is still going to be same. So the kilometers, meters, how long this wire is not going to change. Speed of light is also not going to change. What is there in transmission delay? Bits and bandwidth. Is bandwidth going to change? No, the network is still the same. You're still going to get 1 Gbps. Is bits going to change? Yes, because before we used to transfer 5,000 bits. Now we just have to wait for 128 bits and we can transfer that. So actually, So let's say delay of one link in new system is cut through. So you do propagation. So propagation will not change. Propagation delay plus new transmission. Transmission. And so what is that new transmission delay? So for the first one, the sender will send everything, right? And then when so what's going to happen? 5,000 bits is going to be sent here. Then this is only going to so in this link is going to be, let me take another. In the first link, you're going to send the full first 5,000. So let's just write 5K. In the second link, you're only going to send 128, right? Because this will not wait, this switch one will not wait for all 5K to come. It gets 128, it'll send it. Switch 2 also will do the same thing. Only 128 is going to pass. Switch 3 also 128 will get. Right? So the new transmission delay is actually going to be one old transmission delay for that first link plus the new cut through delay. What is the old transmission delay? We have calculated it before. It says 15 microseconds. What is the cut through delay? So again, bits, we have 128 bits. Bandwidth is how much? 1 GBP bits. So 10 raised to 9. How much will that give us? So it's actually 15. If you see 15 plus 0.128. Oh, so no, so it's a conversion between micro. So micro 10 raised to minus 12 and 10 raised to 9. So how do we do this? We could convert everything to nanoseconds, or we could convert to so we could convert to microseconds. So let's do 15 and 28 nanoseconds. Let's leave it at that. We'll come back to that. And the propagation delay, propagation delay. How much is that? Will not change. 10 microseconds. 10 microseconds. So let's solve this. How would we solve something like this, right? So we could write it as 15 microseconds plus, so nanoseconds we could convert it to micro, so 10 raised to, it's going to be 0.128 microseconds because, so 10, this is 10 raised to minus 9, we 10 raised to minus 9 nanoseconds, we add 3 more and we get microseconds. So this total is going to come to 15.128 microseconds. Propagation delay is also in microseconds. Now what do we need to do? Total delay, total delay from FBS to LVR. So is something that you need to look at. So delay of one link is not going to be one link actually. So the first link, this is little mistake in how I worded it. But the first link, 5K, that's going to take the proper 15 microseconds. So let's look at that. Link one, it's going to take 15 microseconds. How much is link two going to take? It's going to take this new 128 divided by 10 raised to. So let's add it with, so propagation delay 10 microseconds plus transmission delay. How much is the transmission delay here? 15. So 15 microseconds, 25 microseconds. In link 2, propagation remains the same, but here, what is the transmission? 0.128 microseconds. 10 into 128. Link 3 and link 4 are going to have the same thing. 10.12. So now we can write the total delay from PS to LVR. So that's going to be 25 plus 10. So this is 3 into 10.128. That is the answer. Microseconds. 55 microseconds. Right? Because we took, is it 3? So 1, 2, 3. Yeah, it's 3. Yeah. Okay, so that's how we solved it. Now all that we need to do, let's just look at everything again. So we were asked to calculate latency, first bit to last bit. They gave us a single switch. That is this. We were able to calculate. So basically, transmission delay, we know what that is. We multiply that by 2 because there were two links here and here. We got this when there were 3. There were 4 links. 3 switches, there were 4 links. So we multiplied by 4. We got this. And when there's cut through delay, so you have different bits that are traveling in different places. Correct? So for the first link we calculated, it's going to be the UL 10 transition delay. So actually, so let's not. This is not the new transition. This is the cut through delay. The cut through delay is this 128 nanoseconds. Propagation delay is going to be the same. So 5K, you have the 10 microseconds propagation delay, it is 10 microseconds, yes, plus the delay of one link, the transmission delay. Also, see, so it's not 15, it's 5, not 15. Yeah, sorry. So propagation delay plus transmission delay, but link 2, 3, and 4 have their transmission delay as cut through delay. That makes sense. So propagation delay plus a transmission delay, propagation delay plus a new transmission delay, and same for 3 and 4. Then we add it all together. We get 45.384. 384 what? Microseconds. So that's the answer. So I think so. This is the part that's a little bit difficult, but if you're careful, but how much needs to pass through each link, you'll be able to do it. And this also needed a diagram. This question. Okay, I think we have come to the end of today we've run out of time, so I will stop recording now.